Ever wonder what the real difference is between a Python script that just kind of works and a program that's genuinely solid? Well, that's what we're diving into today. We're going to boil Python down to its absolute core logic, focusing on the key ideas that you can start using right away.
And look, this isn't about memorizing a bunch of syntax. It's about really getting the principles that take your code from a simple script to something professional, something robust you can actually build on.
So here's our game plan. We'll start with the basics of data, then teach our code how to make decisions. After that, we'll get into automating tasks, picking the right data containers, building reusable code, and finally, making sure our programs don't fall apart in the real world. Let's get started.
First things first, handling data. We have to start here. This is the absolute bedrock, the atoms of all programming. It's just how Python stores a piece of information, whether that's a number, what we call an integer, or some text, which we call a string.
And this right here, this is the first trap every single new programmer falls into. See, the input function always thinks the user gave it text. So if you ask for 10 and 20 and just add them, Python smushes the text together and you get 1020. It's not doing math. You have to explicitly tell it, hey, treat these as numbers by wrapping them in int. Getting this wrong is basically a rite of passage.
Now, once you have actual numbers, you can do some cool stuff. Beyond your basic plus and minus, the modulo operator, that little percent sign, is a secret weapon. All it does is give you the remainder after you divide. So what's left over? It's the classic way to check if a number is even or odd, but honestly, it's a super powerful tool for finding all kinds of patterns in your data.
All right, so we can store data. Now what? Well, we have to use that data. The next logical step is to start making decisions. This is where we stop just giving commands and start giving our program a brain.
And when you're making decisions, this is a huge one. And versus or. Think of and as a really strict checklist. Every single item has to be true. So in our loan example, even with $1 million salary, you're rejected because you're not an existing customer. But or is way more relaxed. Only one condition needs to be true. That huge salary is enough, so you're approved. Getting this simple difference right can save you from some massive logic bugs down the road.
Okay, making one decision is great, but what if you have to do something 100 times? Or 1,000,000? You're not going to write the same code over and over again. That would be insane. No, we want to automate it. And for that, we turn to the workhorse of all programming, loops.
So, which loop should you use? Well, a for loop is your go-to when the repetition is predictable. You know exactly how many times you need to run, like going through every single item in a grocery list. A while loop, on the other hand, is for when you don't know when to stop. You use it when you're just waiting for some condition to be met, like a user finally entering the right password.
But there's a danger with while loops, a nightmare scenario called the infinite loop, where your program just runs forever. To avoid it, you need two things, no exceptions. One, you need the starting condition. And two, this is the part people always forget, you absolutely must have something inside the loop that changes, that moves you closer to the finish line. If you forget that little I equals I plus 1 part, your program will just hang forever.
So as your programs get more complex, you're not just dealing with one number or one name at a time, you've got collections of stuff, and you need a smart way to organize it all. You need containers.
Python gives you three main options here. A list is your flexible general-purpose workhorse. It keeps things in order, and it doesn't care if you have duplicates. Then you have a set, which is all about two things, uniqueness and speed. It won't allow any duplicates, and it is incredibly fast for checking if something is in the collection. And finally, the dictionary. This is for structured data. You store everything as a key-value pair, kind of like a Rolodex or a user profile. It's built for looking things up instantly by their key.
All right, we're moving up a level now. We're getting past just writing lines of code and into actually designing things. It's time to stop rewriting the same logic and start building reusable blueprints that you can use over and over.
And probably the single most important concept at this stage is understanding the difference between print and return. When a function prints something, that value just shows up on the screen and then, poof, it's gone. It's a dead end. But when a function returns a value, it's actually handing it back to you. You can catch it, store it in a variable, and use it later. That's what makes a function a true, reusable building block.
Now for the big one. Object-oriented programming. It sounds fancy, but the core idea is pretty simple. Think of a class as a blueprint. For example, a laptop class isn't an actual laptop. Nope, it's the design document that says all laptops must have things like a screen and a keyboard, and they must be able to do things like turn on.
So if the class is the blueprint,
Then an object is the actual thing you build from that blueprint. It's my specific HP laptop with its serial number or your specific Dell laptop with yours. Each one is a unique instance that was created based on the rules of the laptop class. And this leads to a really important distinction. An instance variable, like a serial number, is unique to each individual object. My laptop's number is different from yours. But a class variable is shared by every single object made from that class. So if we decide all our laptops will use a USB-C charger, we can set that at the class level, and every laptop object we create will automatically know it.
Okay, so you've designed this beautiful, elegant code, but the moment it meets the chaos of the real world and real users, things can go wrong. So let's talk about the final steps to make sure our code is robust enough to survive out there.
You're generally going to run into 3 kinds of errors. Syntax errors are just grammar mistakes. The computer catches them right away. Then you have runtime errors or exceptions. These are the party crashers that happen while the program is running, usually because it got some data it didn't expect. And then, the programmer's worst nightmare, the logical error. The code runs perfectly fine, no crashes, but the answer it gives you is just flat out wrong. So to deal with those runtime errors, Python gives us this awesome tool called the try-except block. Think of it like a safety net. You put any code that might be a little risky, that might fail, inside the try part. If something goes wrong, the program doesn't crash. It just gracefully jumps over to the except part, where you can handle the problem without bringing everything down.
Finally, working with files, there are 3 golden rules. First, always open the file in the write mode. R to read, W to write, or A to append. Second, be super careful with write mode, because it will completely erase whatever was in the file before. And third, and this is the most critical one, you must always close the file when you're done. .close is what actually saves your changes to the disk. If you forget it, you can lose all your work. So when you put it all together, the real lesson here isn't just a list of commands. It's about understanding the trade-offs. It's about developing the instinct to know why you'd pick a set over a list in a certain situation, or realizing that return is the key to making your functions into real, powerful building blocks. That's the leap from just scripting to actually engineering software.
And that leaves us with a final challenge to think about. Now that you've seen how classes and file handling work, how would you design a class that's smart enough to automatically save its own data to a file anytime you create a new object or change an existing one? It's a great puzzle for connecting these big ideas and thinking about how to make your programs remember things even after they've been closed.